This is the bell work slide. There is no bell work today, so we're just going to pause it here, and we're going to resume when kids have their notes on their desk and are ready to go. Hey, welcome to chemistry. This is your teacher, Mr. Dawkin, and you have entered Unit 17, which means you are in the last unit of this year. Congratulations. We are almost there. Hang in tight. This is going to be nuclear chemistry, and it's probably my favorite unit of all the whole year. So fasten your seatbelts. Let's get to it. Nuclear chemistry. A couple people you need to know about. Number one is going to be Antoine Becquerel. So I want you to underline this guy's name. In 1896, Mr. Becquerel discovered something called radioactivity. How did he do it? Well, he accidentally, it was an accident, he left a uranium ore, which is the element U, number 92. Atomic number 92. He left it on top of some photographic plates. You know those old school things where you basically have to develop photography? Well, he set it on those plates, left it there for a while, and it became fogged up. And he was like, what the heck? What's going on here? He eventually figured out that it was something called radiation. And that's what we're going to learn about today. Nuclear chemistry. It has everything to do with radiation. Becquerel had two students that helped him, Marie Curie and Pierre Curie. So we're going to learn about them a little bit later too. And at the end of Unit 17, once we take our test, there's going to be a project that we do, and some of you may be studying Marie and Pierre and possibly Antoine Becquerel too. All right. What did the uranium do to the photographic plates? Well, he left it on there, and straight up, the plates became fogged up. And that's how he knew that something was up. It wasn't right. He had never seen anything like it before. So, what is radioactivity? Okay, radioactivity is actually a property. So I'd like you to circle this in your notes. It's just a property. It's a property by which uranium, really, or any element, gives off rays, which, I want you to write this in, can also be classified as energy. Energy rays, kind of like on the electromagnetic spectrum. Kind of like X-rays, microwaves, radio waves, things like that. So that's what we're talking about, radioactivity. Radiation is kind of the noun, the actual thing that comes off, the penetrating rays that are emitted by a radioactive source. So let's look at this picture over here real quick. This is going to be the nucleus, hence nuclear chemistry. We're not looking at the electrons like we were in redox. We're looking at the nucleus, where the protons and the neutrons are. You'll notice that a particle gets shot out. Okay, shot out. We call this nuclear fission, which we're going to learn about. When that happens, a bunch of energy gets released. Together, the particle and the energy, we call that radiation. So in 1903, the Curies and Becquerel, they won a Nobel Prize for discovering radiation. So, in 1903, Nobel Prize, what was it for? Radiation. They had no idea what it was, but they discovered it. Marie Curie is still the only woman to win the Nobel Prize in both chemistry and physics. So there's something I'd like you to write on your notes, and it's this right here, boss, because she is a boss woman. And we're going to learn a little bit more about Marie Curie in the future. All right, radioisotopes. A couple of things to know. Well, it has the word radio in it, so we're talking about radioactivity. And then it has this word that we learned in actually Unit 3 called isotopes. So these are isotopes that are radioactive. They have unstable nuclei. But let's go back. Let's label something real quick. I want you to write this in your notes or just draw an arrow like this. Isotopes have a different number of protons and neutrons. Go ahead and write that in. That's what we learned in Unit 3 when we did the Candium lab with the beans. Remember that? It's been a while. The stability of a nucleus is determined by its ratio of protons to neutrons. So we know that an isotope is something that has a different number of protons and neutrons. So an unstable nucleus is something that's going to lose energy by spontaneously, that means delta G is negative, emitting radiation. This is called radioactivity. So all nuclides with atomic numbers greater than or equal to 84, which is element, I want you to write this in, polonium. This is polonium. It's right ahead of bismuth and lead. Light nuclides, so aka like light things that don't weigh much, okay, the nuclides that are less than 84 are stable when they have a neutron to proton ratio of 1. So let's pick, let's pick lead, Pb, at element 82. It has 82 protons, which means it's going to be stable if the nucleus also has 82 neutrons. Now, let's talk about heavier nuclides. Heavier nuclides are stable when the neutron-proton ratio is greater than 1. So, for instance, let's look at, oh gosh, radon. Let's go Rn, radon. That's element number 86. It is greater than 84. So, it's going to have, let's say that it has 86, well, let's change that. Let's say that it has, we know that it has 86 protons. So to be stable, it has to have a ratio greater than 1 of neutrons. So it's going to have maybe 90 neutrons. Nuclides with even numbers of protons and neutrons are more stable than those with odd numbers. So overall, if you want to be stable, you need to have the same number of protons as you do neutrons. That's just kind of the way it goes sort of a deal. So this is called a table of nuclides. I'm not going to stay here for long, but I do want to show you this. Check out each row. Look at the top row. It's all titanium. Look at this row. It's all magnesium. This one's all oxygen. So each row has a different element. So why are there so many different elements? Well, if you notice, the atomic number, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, it has a bunch of different protons. So the number of protons, titanium has the same number. So titanium has 22 protons, but you'll notice that the number of neutrons is changing. So these are all isotopes. We call it a table of nuclides because we're focusing specifically on the nucleus, but they are isotopes. You'll notice that some of them have different colors. And what you'll learn is that different isotopes behave differently depending on how stable they are. So maybe the blue ones here in the middle, these are probably the most stable. They probably have, a good amount of stability. They don't produce radiation or radioactivity. So this is called a table of nuclides. If we zoom out, we know that there are 118 elements on the table. So here's the entire chart. Each row shows you a different element. So if we go up, 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 we get to element 84 in here, which would be polonium. And you notice if you go over, and it's not perfect, somewhere in here, all of the black dots, the black squares, these are all stable isotopes, meaning they don't produce radiation, they don't release energy. But look what happens when you get to element 84. Remember what we talked about? Yeah, stability is lost. Check it out. How many black dots are there? Yeah, there's a couple, like right in there, but otherwise, nothing is stable above 84. These are all the man-made elements. So usually, if you look at all the white elements on my periodic table, those are all man-made elements. And you'll also notice that element 43, which is technetium, and it's actually right here. There are no black dots for technetium. Number 43, it's an unstable element. Would plutonium be stable or unstable? So plutonium is Pu, and that's going to be element number 94. So what would you say? Stable or unstable? It's greater than 84, so unstable for sure. Why? Because it's greater than 84. All right, so a couple things you need to know before continuing with nuclear chem is this right here. You're going to have to be familiar with these symbols. You're going to see element symbol like carbon, and then you're going to see a smaller number, which is the atomic number. Usually that's on bottom. Doesn't have to be. Sometimes it can be on top. On my periodic table, it's on top. The bigger number is the mass number. And I want you to write this in. Find a space in your notes. Mass number is protons plus neutrons. That's how we find the mass number. Okay. So you add up 6. We know the total's 12 here. So to find the number of neutrons, we did this in Unit 3 a long time ago. You just have to figure out what plus protons and neutrons equals the mass number. So go ahead and write that down in your notes. You'll need that formula at some point or another. Some of you probably still remember it. Okay, there are 4 types of radiation that we want to cover, and that will pretty much finish it out for today. Number 1, alpha. Circle it, fill it in. I want you to write this symbol in too. Okay, it kind of looks like a Jesus fish. but it's not. It's the Greek symbol alpha. Okay, alpha radiation. Alpha releases a helium nuclei, okay, emitted from a radioactive source. 2 neutrons and 2 protons, because that's what helium is. I want you to write this in as well. Helium, 4, 2. It's got it's got 2 protons, and then the mass number is 4. So it's actually releasing a helium atom. What happens? Well, it goes from plutonium down to uranium. Check it out. The mass went down by 4, minus 4, and the protons went from 94 down to 92. A 4 and a 2, well, that's a helium atom. Where did it go? It went down here. It's got a 2+ charge, okay, because all it is 2 protons and 2 neutrons. There are no electrons. We're literally just talking about nucleus particles. It doesn't travel very far. This is the weakest type of radiation, and they don't penetrate your body very much. They can be stopped by a sheet of paper. They can't penetrate your skin, but they are dangerous if they're ingested. So let's say you ingest some of this plutonium. I don't know where you'd get plutonium, but it would hurt you, okay, from the inside. But your skin's tough on the outside, so you're not harmed if it's just near you. Very common with heavy nuclides. Okay, heavy nuclides. Remember, heavy nuclides are the ones that are larger than or equal to 84. So you're going to be seeing some equations like this. Here's 1, here's 2. Let's do the first one. You have the element uranium. So right away you can look at your periodic table and fill in at least the number of protons. If you look at number 92, you'll see that it has atomic number 92. Now, up top, we can't necessarily put a mass number on it because what you'll see is 238.029. Remember that this is an average atomic mass. This is not a mass number. This is the average of all of the isotopes, and you did this in your Candium lab. So we can't put 238.029 on there. That just doesn't make sense. But what we can do is use our equation. Helium, we know that this is alpha radiation from the helium particle. 2 protons plus 90, so 90 plus 2 is going to give us 92. Well, we already figured that out, but it makes sense. So how about up top? 4 plus 234 is going to give us 238. So we're not really balancing chemical reactions, but what we are doing is making sure that the particles are balanced. So can we figure out what element is this blank? Well, it has 90 protons, so you just have to look on the periodic table. 90 is Th, which we call thorium, which is definitely the Avenger element of the periodic table. I mean, come on, Thor is pretty rad. All right, next one, radium. 226 over 88 yields. There's a radon and a helium atom, so I'm just going to fill in the blank. 88 and 2, well, what has to be here? 2 plus what gives me 88? That's got to be an 86. Radon. Makes sense. It's on the periodic table. 4 plus what gives me 226? That's going to be 220, what? 222. Bingo. And that's all you're doing. This is called alpha radiation. I am going to continue on another video. Okay, so what we need to do is exit out here and go to the other video that I have created so that we can finish off. We have 3 more types of radiation. Okay, so hit the pause button and let's switch on over to that other video.